Today, let's forget about the AI that writes poems or makes funny pictures. We're going to talk about a totally different kind of AI. One that's built for the really high-stakes world of physical systems. Think power plants, airplanes, you name it. This is AI for the real world.
And when I say high stakes, I am not kidding. Let's ask a question that sounds like it's straight out of science fiction. Can an AI actually help us contain the power of a star right here on Earth? It might sound crazy, but this is the ultimate engineering challenge.
Because, that's basically what a nuclear fusion reactor is trying to do. It's trying to control plasma that is burning at 150 million degrees Celsius. To put that in perspective, that is 10 times hotter than the core of the sun. The engineering required here is just almost beyond comprehension. And here is the absolute crucial point. The AI that you're used to, the one on your phone or your laptop, it is fundamentally completely unequipped for this job. It has a massive, dangerous blind spot when it comes to the physical world.
So, first up, let's dig into exactly what makes this problem so, uncontainable, and why the AI we have today just can't get its head around it.
So inside one of these Tokamak reactors, you've got this superheated plasma. Now, obviously no material on Earth can touch it, so it's held in place by these unbelievably powerful magnetic fields. We're talking strong enough to literally lift an aircraft carrier. But here's the thing, the plasma is always restless. It's constantly looking for the tiniest weakness, any microscopic flaw in that magnetic cage. There is absolutely positively zero margin for error.
And that brings us right to the core flaw in standard AI. It basically suffers from a kind of 3D blindness, and that makes it dangerously unreliable for any kind of physical task.
To really get this, there's a great analogy from the source material about a dog named Slob the Dachshund. If you ask a normal AI to draw Slob from the side, it'll probably do a fantastic job, right? Why? Well, because it's seen millions of pictures of dogs from the side. It's just recognizing and repeating a pattern.
But now, here's where it all falls apart. Ask that same AI to just rotate Slob by 45 degrees, and you get complete gibberish. You might get a tail growing out of his nose. This simple little rotation proves the AI has no real understanding of what a dog is. It doesn't know that a spine connects to a pelvis, or what up and down even mean in the real world. And this gets to the heart of the problem. Standard AI flattens the entire world into a one-dimensional list of data points. It just learns statistical tricks, like which numbers tend to appear next to other numbers. But reality isn't a list. It's a 3D geometric structure. It obeys the laws of physics, and it has inherent shape and direction.
Okay, so how on earth do you fix that? Well, the solution is to build an AI that can actually speak the native language of the physical world, and that language is physics itself.
And this solution is called geometric AI. Instead of flattening everything into a list, it uses something called a graph neural network to see the world as it actually is, a web of different objects, and all of their 3D relationships to each other.
There's this brilliant high school gossip analogy to explain it. Think of students as nodes and their friendships as the edges connecting them. Now, some facts are scalars. They have a size but no direction, like a test score. If you rotate the school, Andy's score is still 42, right? But other facts are vectors. They have direction, like Abby walked left. If you rotate the school, the direction she walked changes. Geometric AI is built to understand this fundamental difference.
And the results? They're just staggering. An engineer used a geometric AI to predict the incredibly chaotic turbulence over an airplane winglet, and it got it right with 98% accuracy. It could do this because it natively understood the physics, the pressures that don't change with rotation, and the velocities that do. It perfectly preserved the geometry of the problem.
But okay, here's the next big hurdle. Getting the right answer is one thing, but for systems where lives are on the line, you have to be able to prove that your answer is safe and reliable. A correct guess just isn't good enough.
The author actually shares a personal story about a research grant they applied for that got rejected. They had a model that worked great, but they couldn't systematically prove to the reviewers why their specific mathematical approach was the best one. It really highlights a core truth. Just because something works doesn't mean you can prove it's safe. And empirical success is not a verifiable proof.
So to solve that, we need to understand how systems can think. You've got deduction, which is fast but rigid. It just follows rules it's been given. Then there's induction, which is what most machine learning does. It sees millions of examples and guesses a rule, but we don't know why. It's a black box. But then there's a third mode, abduction. This is like a detective's reasoning. It works backward from the evidence to find the most likely explanation. And that abductive, detective-style reasoning, that is the key to the ultimate solution. It's a system that can discover and then prove the best possible math for a problem all before it ever goes live.
So meet XRAG, the Extreme Reliability Axiom Generator. The concept is just brilliant. It works completely offline, like a detective examining a cold case. It takes all the data, uses that abductive reasoning to find the best possible mathematical formula to explain it, proves it's the right one, and only then does it freeze that proven formula into a simple, safe rule for a live system to use. There's no guessing in real time, ever.
And XRAG is super methodical. It works through 5 layers. First, it characterizes the data. It figures out its properties, like if it's non-stationary, which just means its stats change over time. Then it pulls from this huge library of math options, throws out any that don't fit, fine-tunes the best one, and finally, and this is the magic part, it generates a report for a human to read that explains exactly why it made its choice. It removes all human bias and old habits.
And here's what that looks like in the real world. When you're analyzing noisy data from sensors in a nuclear plant, humans usually just default to a method called a Fourier transform. It's what we know. But XRAG proved that for this specific type of data, a different method, a wavelet transform, was mathematically better. The result? It reduced the data scatter by a massive 67%.
And that wasn't a fluke. In another case, modeling how heat spreads, XRAG avoided an easy but unstable mathematical method a human might have picked. Instead, it chose a more complex but fundamentally stable one. And by doing that, it cut the model's error by 63%.
So, when you combine these two breakthroughs, an AI that actually understands 3D space and a system that can prove its own math, you unlock an incredible future. A future where we can simulate and prevent failures before they even have a chance to happen.
This all leads to the concept of a world model. Basically, it's a system that lets the AI play out future scenarios in its head. It can simulate the physical consequences of its actions based on the laws of physics before it actually does anything. It's a huge shift from just reacting to what's happening now to accurately predicting what's going to happen next.
This really brings us to a whole new era, an era where catastrophic engineering failures aren't just something we react to, but are things that are simulated, diagnosed, and prevented inside a computer. So I'll just leave you with this question. What really changes when the machines all around us can perfectly understand and simulate the physics of what they're about to do before they even move a single millimeter?